What's up, everybody? In this video, we're going to cover USACO's 2019 February contest at the silver level, problem number 3, the Great Revegetation. A lengthy drought has left Farmer John's end pastures devoid of grass. However, with the rainy season arriving soon, the time has come to revegetate. In Farmer John's shed, he has exactly 2 buckets, each with a different type of grass seed. He wants to plant grass in each of his end pastures, choosing exactly one type of grass to plant in each. Okay, so he's got a bunch of different pastures, and he's going to plant either type 1 or type 2 of grass in every pasture. Being a dairy farmer, Farmer John wants to make sure he manages the somewhat particular dietary needs of his M cows. Each of his M cows has 2 favorite pastures. Some of his cows have a dietary restriction that they should only eat one type of grass consistently. Farmer John therefore wants to make sure that the same type of grass is planted in the 2 favorite fields of any such cow. Other cows have a very different dietary restriction requiring them to eat different types of grass. For those cows, Farmer John, of course, wants to make sure their 2 favorite fields contain different grass types. Please help Farmer John determine the number of different ways he can plant grass in his end pastures. Input formats. First line of input contains N and M, N being the number of pastures there are, M being the number of cows there are. Each of the next M lines contains a character that is either S or D, followed by 2 integers in the range of 1 to N, describing the pair of pastures that are the 2 favorites for one of Farmer John's cows. If the character is S, this line represents a cow that needs the same type of grass in its 2 favorite pastures. If the character is D, then the line represents cows that need different types of grass. Output format. Going to revegetate.out. So just as a reminder, this means you're gonna have to read from a file and write to a file rather than the console. And if you're not familiar with that process, I have a video that goes through making file readers that you can watch prior to doing this. Output the number of ways Farmer John can plant grass in his N pastures. Please write your answer in binary. Okay, so the binary, this is important because a lot of people missed that part and just wrote it out in decimal, or we're trying to figure out how there were 10 different ways. This actually makes it easier. I'm going to explain why in a second here. So let's go ahead and write this out. I have 3 pastures, 1, 2, and 3. We don't necessarily have to build a graph with this, but it is kind of a graph. There is a cow between 1 and 2. Let me number these 1, 2, and 3. There's a cow between 1 and 2. So right there. That is S. That indicates that nodes 1 and 2 should be the same. And there's a cow between 2 and 3 here that is D, which means that cow should be different. Now, I don't think it specifically states in the instructions whether or not it's possible to have another cow that is also 3, 2. It turns out it doesn't actually impact the problem because the number of ways we can plant the grass are going to be set. The way you're going to write your code, though, is you do need to be aware that if you were to have something like S32, then we've got an improbable situation. Likewise, if I were to have a S31, that's not possible. And the reason why is because if 1 has to be the same as 2 and 2 has to be different from 3, then 3 could not be the same as 1. There's no solution for that. So we do have to watch out for these situations. I'm not sure which or how many of them are in the test cases, but because it's not explicitly stated, we have to make sure that we don't have an impossible situation. And if we do, I assume we just put out a 0. So what we've got here is, and actually the code I wrote passed all the test cases, and I accounted for that, and I didn't have any issues. So yeah, as long as you were accounting for the possibility of an impossible graph and not putting zeros, that's sufficient. But again, I don't know if they're going to give us any impossibles or not. I haven't gone through all the test code cases one by one and looked at the input and output. Same 1, 2. So for example, if this is grass type A, this also must be grass type A. If that's grass type A, then node 3 has to be grass type B, and then we're done. So that's one way to do it. But if I had done B for the first grass type, then that means that this would have to be the same, which is B, which would mean this has to be different, which is A. And that is a second way to do it. The number 2 written in binary, if 1 is this, 2 is that. Then this would be 3, this would be 4, and so forth. So because of how this is set up, whatever I start here, if this is a valid structure, whatever I start here, if I can find my way all to the end, then I know that if I were to start with A, that also would have a valid solution of just inverting all the letters, because there's nothing specifically significant about grass type 1 or grass type 2. So whichever grass type you use here, whether it's 1 or 2, for the first field, if you can fill out grass types for all of them, that means there's exactly 2 solutions. And there have to be 2 solutions. And the reason why there have to be 2 solutions is because you could start with either one of the 2 grass types and still have a valid solution. If one is valid, the other must be valid. Let's throw a completely new set of pastures. Let's say like this was a 5. And let's say like I have same, but it doesn't even matter, between 4 and 5. So down here, I've got 4 and 5, and those are the same. So, you know, whatever goes down there. Now, if I know that this chunk up here has 2 solutions, one is AAB and one is BBA, this one down here also is going to have 2 solutions. I can either make them both A or I'd make them both B. So every valid connected little network here has 2 possible solutions just because of the setup of the problem. Whatever you choose for your first type here, if you can fill out the entire little subnetwork here and it's valid and there's no conflict, then that means that there's 2 solutions. One where you start with the first grass type, one that you start with the second grass type. Which means that if I have 2 solutions here and I have 2 solutions here, then the number of solutions I have is 2 times 2, because I've got either of 2 solutions here and either of 2 solutions here. So if I have solution, you know, I don't know, solution X, solution Y, and then solution Z and solution W, then I would have XZ, XW, YZ, and YW for each of the 2 grass types. Or if I use the grass types, it makes more sense. If I have the solution where the first grass type is A and the solution where the first grass type is B, and here I have the solution where the first one is A and the first one is B, just being the first, whatever I picked for the first one, then I have AA, AB, BA, BB. That's 4 possible combinations. 4 in binary is 1, 0, 0. So when I had only 1 field, my answer was 1, 0. When I have 2 fields, my answer is 1, 0, 0. If I were to have a third one over here, say like 6 connecting to 7, then that would be yet another 2 solutions. And then I would have times 2 again, which would be 1, 0, 0, 0. So for the binary part, we don't actually have to do any binary. We just need to put out a 1 followed by however many zeros, which matches however many different separate networks there are. So however many separate networks there are, that's how many zeros you have. If you have 1 network, it's 10. If you have 2 networks, it's 100. If you have 3 networks, it's 1,000, 1, 0, 0, 0. If you have no networks at all, or if none of your networks, if at least one of your networks is invalid, for example, you know, again, like we had earlier, if I had a connection between 1 and 3 that has to be the same, this is an invalid network, which means there's no possible way to plant the grass, and the output would simply be 0. So let's talk about how we're going to actually approach this problem from a coding standpoint. You're going to probably want to do a recursive depth first search. This problem involves putting these different fields into groups and keeping track of what group each of them is in. So the first thing I did is I built my network. The way I did that is I did an adjacency list. You'd be using vectors if you're in C++, or if you're in Java or Python, you'll want to use a list that you can just append to the end of or add to. So the first thing you want to do is build your adjacency list. So for each of the nodes that exists, we're going to put back essentially 2 pieces of information. We need to know where can you get to from this node and whether or not that node needs to be the same or different. For Python, I would recommend a list of tuples. For C++, you could do a vector of pairs. For Java, I think I have a video on dealing with situations where you have pairs, or you could just do a list of lists, or you could make a custom data type that has 2 variables. One would be the destination node, and one would be whether or not it needs to be the same or different. So essentially what you're doing is node 1, I see here that I have an S between node 1 and 2, which means node 1 has a neighbor node 2 that has to be the same, and node 2 has a neighbor node 1 that has to be the same. And then I have different 3, 2, which means 3 has a neighbor 2, which has to be different, and 2 has a neighbor 3, which has to be different. Okay. So once you have that set up, essentially what this is going to allow you to do is quickly check any node and see where you can get to from that node, what the neighbors are. So 2 has the neighbors of 1 and 3, 3 has a neighbor of just 2, 1 has a neighbor of just 2. Next thing you want to do is you want to know what your groups are. Let's actually make a slightly more complicated test case. I'm going to throw back in that same between 4 and 5 into our example here, just so we can have a little bit more data to work with. So I'm going to recopy this. I have 1 goes to 2, which is same. 2 goes to 1, which is same, and 3, which is different. 3 goes to 2, which is different. And then I'm going to have 4 and 5 be the same. Clean this up here. All right, nodes 4 and nodes 5. Just to make this a little more interesting, we'll have node 4 going to node 5, which is going to be the same. Node 5 going to node 4, which is the same. All right, and then we'll do one with an impossible graph too. Okay, so I've got connections between nodes 1 and 2. 2 goes to 1 and 3, 3 goes to 2, and then I have 4 to 5 and 5 to 4. We want to know what group each of these nodes is in. So the way I did this is I built a vector. I used C++ when I did this. I built a vector and I put 0 into each one of these. Now what this represents, and there's actually, I guess, one here. We didn't have index 0. What each of these represents is what group is each of these nodes in. What group is node 1 in? What group is node 2 in? What group is node 3 in? What group is node 4 in? What group is node 5 in? And if you need more practice with these, there's a couple problems that are like this. I'm trying to think of the milk visits uses this technique. And there's at least 1 or 2 others that use this technique of the adjacency list. But milk visits in particular is the one that immediately comes to mind. So basically what you have is you have a graph. You've got an adjacency list representing your graph. And then as you go through the graph, you're going to explore and you're going to assign a group to each one of these nodes. Let's kind of draw a little picture of what this looks like. So node 1, 2, 3, then I have 4 and 5 down here. 1, 2, 3, 4, 5, same, different. Okay, so essentially what you're looking to do is you're looking to have a group counter. Your group counter probably is going to start at 0. And then for every node, starting from node 1 and going through nodes 1, 2, 3, 4, and 5, you're going to call a recursive function, passing in that node number, in this case, node 1, passing in some sort of flavor. We can start with flavor. I used flavors 1 and 2. It doesn't really matter what you do, but because we have 2 different graph seeds, we need to make sure this network is valid. So as we go through, we're going to assign flavors to the nodes. And then if we hit a situation where we hit conflict, then we'll know that it's an invalid problem. And as long as we are able to flavor everything, we'll know we have 2 results per network. And then the number of groups will be the number of separate networks we have. So have flavor 1, I called it. And then group number 1 now, because this is the first group. Here, what I have is representing what group each one is in. Let's go ahead and right above that, I'm going to write what flavor each one has. So I'm going to start with flavor 0 for each of these as well, just to save some space. You're probably going to want, again, either you could do another vector of pairs where 1 is the flavor and 1 is the group that it's in, or you could just do 2 separate vectors. You have a flavor group and a flavor vector and a group vector. So what these zeros represent right now is that 0 is not in a group yet and does not have a flavor assigned. So when I call f of 1, 1, 1, I'm saying I want to assign node 1 to group 1 and also flavor 1. So that's fine. I go in here. I'll change these to 1 and 1. Now what I want to do is I want to iterate through all of the neighbors of group 1. And for each neighbor, I want to check to see if it has a group yet or not. If it doesn't have a group, that means it also doesn't have a flavor, because I've never assigned it a group and I've never visited it, which means I have no flavor for it. So in this case, I have my for loop. For I from 0 to however many neighbors node 1 has, which in this case is 1 neighbor, then I'm going to call f of whatever that node is. So for example, in this case, 2, same group number. And then I got to look at this. And if this is an S, I'm going to do the same flavor. But if it's a D, I'm going to change that flavor from a 1 to a 2. So in this case, because this is an S, I want to do same flavor. So I've now got node number 2 being placed into group 1, same group, with flavor 1. So that's going to change both of these 2s to 1, or both of these 0s to 1s in the 2 section. And having now done that, I now am going to iterate through all of the children, all of the neighbors of, clean this up a little bit, all of the neighbors of node 2. So looking at this, I see node 2 has 2 neighbors, neighbor 1 and neighbor 3. So I'm going to do a for loop again for I from 0 up to, the number of neighbors 2. I want to check to see if I should go to that neighbor. Now, I've got 2 possibilities. If I have no group, such as, for example, the case of 3, I'm going to recursively call that. So that'll be the f of 3. We're going to do the second one first. F of node 3, still group 1, but because this is a D, I have to change the flavor. So because right now I'm on f of 2, 1, 1, I have to change the flavor from flavor 1 to flavor 2. And that'll be the f call for node 3. So because on the f call for node 2, here, I have a neighbor here that is supposed to be a different flavor. We're still in the same group because it's still connected, but we're going to change the flavor. So F312. That is then going to go into 3. It's going to make it part of group 1, but it's going to make it flavor 2. And then the other one is this F15. Now, because of the fact that node 1 already has a group, I need to make sure that the flavor that I just assigned to node 2, which is here, matches the flavor of node 1, which is here. Now, the reason we want to double check that is because we might have a loop. It's entirely possible that there might be a cow we talked about earlier between 1 and 3. If that was the case, for example, if I had a same here, then I would have a third neighbor over here. And what's going to end up happening when I call that, no, that actually would be a second neighbor on 3, sorry. That would be here. If that was the same, then I would have a connection from 3 to be the same. And then what's going to happen when I get to that is on my recursive call for 3, which is right now, you can see F312. Let me clear this out. F312 would go through and check all the neighbors of 3. So it would do 2D. It checks 2. It knows that it's flavor 2. It checks flavor 2, node 2's flavor and sees it's flavor 1. So that validates the D. We do have to check if it already has a group to make sure that there's no conflict on the flavor. So when I'm on my F of 3 call, I check that I am flavor 2. I know that that node 3 connects to node 2. So I have to make sure that these are different. And they are different, so that's fine. In this case, this is where I added this bad connection here. When I get to this one, that should have been a 1. Actually, 1 same from 3. 3 to 1 same. When I get to that, then I look at node 1. I see node 1 already has a group, and I see an S. That indicates that there is a cow that between nodes 3 and node 1 needs the same flavor. Right now I'm on flavor 2. I check the flavor of node 1 and I see that that's invalid. As soon as I detect an invalid, the program's over. Because if there's a particular circuit where I can't plant grass, then I have no solution. So if you want to have like a global Boolean and just set it to false or set it to true or whatever to let it know that it had a failure, that would be totally fine. And that's basically what I did. I had a Boolean variable that starts off as false and I called it failed. And then when I get through the test, if failed ever got turned to true, that meant that I hit a situation where I have a neighbor. In this case of this example, a neighbor is 1. I have a neighbor that has a different flavor from the flavor that I'm trying to assign, but is supposed to have the same, or that has the same one when I need to have different. But if we don't have this, that's not going to happen. There's no function call to that. And then what's going to happen there is that's going to be the end. This neighbor wouldn't exist. We would iterate through. We would verify that 2 has the correct different flavor from node 3. And they do, because node 3 and node 2 have different flavors. Everything's fine. Then I have no more recursive calls because all of the neighbors now have had a groups assigned. And the only time you recursively call onto a neighbor is if it has no group. If a neighbor, so basically you've got two choices. If the neighbor already has a group, then we just make sure that we're not violating the same or the different thing from the node that we're on in the neighbor. If the neighbor doesn't have a group, we recursively visit that node, assign the group, and assign the flavor. Okay, so that's done. We then would go back to our main that just finished calling that F111, F111. We have one group. We should count that. And then we'll move on to f of 2. F of 2. But f of 2 doesn't need to be called because 2 already has a group. So move on to f of 3. F of 3 doesn't need to be called because it already has a group. So now we get to f of 4. F of 4, node 4 has no group yet, so we'll call 4. We are now into group 2. And again, you can just start with flavor 1. It doesn't matter which flavor you use. So F421 is now our next recursive call. F42. I should probably do a video exclusively about recursion because I know that not everybody knows or is comfortable with recursion yet. Okay, so 421. So basically, I've got a function call saying that I want to assign node 4 to group 2 and give it flavor 1. So I'm going to go into here. Node 4 gets to be group 2 and flavor 1. I then go through all the neighbors of 4, which in this case, the neighbor is 5, and it's same. 5 has no group yet, which means that I can directly call F5 group 2. And then since it's the same, I'm going to keep the same flavor, which is 1, F521. F521 gets up into this function. It's going to assign group number 2, flavor 1. We then loop through here for all the neighbors of 5. We only have one neighbor, and that's neighbor is 4 for same. Because 4 already has a group, we just need to check to make sure that the flavor of 4, which is the neighbor, matches the flavor of 5, which is the node we're trying to assign, since those are the same. And it's the same because we just assigned it, but that's not necessarily always the case. But since they're the same, that's not violated, which means we're good, but then there's no recursive call. That ends the function there. Having now finished, we would go back to the main. We would look to call f of 5, but there's no need to call f of 5 because f of 5 already has a group, and then we're done. So your main has looped through calling this depth first search, this recursive depth first search on every single one of these nodes. Now that that's done, we've guaranteed that every single one of them has a group. If we hit a situation where we had a lockup where we found a neighbor that's supposed to be the same but was different or vice versa, then we just output a 0. On the other hand, if we make it all the way through and we didn't hit any paradoxes, I guess, my group now will be increased to 2 because I've got 2 groups. I'll have exited the loop in the main, and then all I need to do now is put a 1 with however many zeros matches G. So in this case, 0, 0, 1, 0, 0 is equivalent to 4, and 4 would be the number of solutions I have here. One of the solutions would be A, B, A, B. One of the solutions would be A, B, or sorry, this should be A. First one, A, and then B. So it's the second solution with these being the same and these being different. Then I would have B, A, and then again, A, or B, A, B. So those are my 4 solutions. If we look back at the original problem as it was presented here, they didn't have the 4-5 connection. I just added that to make this a little more interesting. But if we didn't have that, this would have dropped out. We would only have the 2 groups, or the 1 group. Number of groups here would only be 1. We'd have outputted a 1 with only 1 0. And then our only 2 ways to plant the grass here would be either A, B, or B, A. So just as a real quick recap, first thing you want to do is build an adjacency list. For every single one of these nodes, 1, 2, and 3, we need to know where they go, a list of every place they can go to. In the case of 1, it goes to 2, has to be the same. In the case of 2, it goes to 1, has to be the same, and also 3 has to be different. In the case of 3, it goes to 2, and has to be different. Once you've done that, in your main section, you loop through and do a DFS, with each node trying to assign it to a group. Try to assign node 1 to group 1. For every neighbor that does not have a group, you give it the same group and you assign the flavor, either being the same flavor if it's an S or a different flavor if it's a D. And then for that node, you loop through all its neighbors and do the same process. Any neighbor that has no group will be directly given a group and a flavor by doing the recursive call. Anyone that already has a group, you just need to make sure that there's not a conflict between what flavor we expect it to be and what flavor it actually is. You'll do that by building probably two lists, one that shows the flavor of each field, which starts off as 0, meaning no flavor, and will get set to 1 or 2, depending on whether or not you give it grass flavor 1 or 2. And again, we only need that just to make sure that there's no conflict. And also the group, which again can start all as 0s. And then as you recursively go in, you'll change those to 1. So in your recursive function, you have 3 values. You have the node that you're currently on. You have the group that you're currently assigning, and you have the flavor that you're currently assigning it to. And then for every neighbor, from 0 up to however many neighbors you have, if that neighbor has a group, make sure the flavor that we just assigned in this function call doesn't match or doesn't conflict with the flavor that we have on file for that neighbor. If on the other hand, it doesn't have a group, then we just recursively call onto that new node, the same group number. And then for the flavor, depending on whether or not it's a D or an S, we're either gonna switch it or keep it the same. So if it was a 1 and it says it's different, then we gotta change this to a 2. If it's a 1 and it says it's the same, we would keep it as a 1. Once we finished, however many groups we have, in this case, we have 1 group, whatever our group is, we print out a 1 together with however many groups we have, we print out 0s, in this case 1, 0, and then just make sure you write that to a file and close the file to submit. So that's how to solve the problem. Good luck coding it, and I'll talk to you on the next one.